In this video, we will learn about the principle behind some of the very basic convolutional neural network architectures that have significantly raised the bar for image classification. So let's get started.
Convolutional neural network architectures. Okay, so let's start with the LeNet-5 architecture. So this was one of the first CNNs that massively inspired the AlexNet architecture, which, as we all know, was the first CNN architecture to significantly raise the bar on the ImageNet dataset. So we already discussed the LeNet-5 architecture in our lecture on CNNs. And if you remember, it was one of the first CNNs that was successfully used in practice. So it uses this 5x5 filters with stride 1 in the convolutional layers. And it has this architecture that you see here, which has alternating convolutional and subsampling layers. And we use pooling here for subsampling. So it uses average pooling and it uses tanh for the activation function. So in most architectures today, I should say that it's more common to use max pooling than average pooling. And we mostly use ReLUs or the other activation functions that came after. So one thing to remember here is that we use valid convolutions here, which reduces the size of the feature maps. So this LeNet-5 architecture worked really well for the digit recognition task, which was also used in the US Postal Service back in the day. Okay, so by now in this course, we have already discussed a lot about the ImageNet dataset. Let's briefly take a look at the ImageNet challenge. And this ImageNet challenge was really a big driving force behind the advances that we see today in the classification architectures. So the ImageNet challenge is called the ImageNet IL-SVRC challenge. And this was basically held annually from 2010 to 2017, and after which it was discontinued. And this ImageNet challenge has many different tasks, such as object detection and classification. And the goal here is to use the ImageNet datasets to perform these tasks. And the ImageNet dataset has 1.3 million training images, and it has over 1,000 different object categories. And today, ImageNet is still one of the standard datasets that's used for pre-training networks for classification or even some other complex recognition tasks. Okay, so chronologically, the next important architecture is AlexNet, and most of you might have heard about the AlexNet architecture, which was introduced by Alex Kishevsky in 2012. So this was the first CNN to do really well on the ImageNet classification benchmark, and it also outperformed all the other non-deep learning based methods by a significant margin. So you can even say that this was the first CNN that started the widespread interest in deep learning that we see today. So AlexNet has this architecture of convolution, max pooling, normalization, and again, convolution, max pooling, normalization, followed by 3 convolutional layers and 3 fully connected layers in the end. And the last fully connected layer basically has 1,000 here. This is because ImageNet has 1,000 classes. So this looks quite similar to the LeNet-5 network that we saw in the previous slide, but just scaled up to go much deeper. So let's briefly take a look at this in more detail. First, if you remember the CNN lecture, AlexNet uses group convolutions, and that's why you basically see these 2 streams of layers here. This is because Alex trained this on the GTX 580 GPU, which only has 3 gigabytes of memory. So they couldn't fit this entire network on this. So they separated this into 2 streams that was individually trained on 2 different GPUs. Okay, so the first convolutional layer in AlexNet basically has 96 11 by 11 filters. So it's basically all these numbers of filters that you see here times 2, because you have 2 streams here. Then we have a max pooling layer with 3x3 filters, and all the max pooling layers almost always have 3x3 filters. Then we have a normalization layer here, and again, a convolution, pooling, and normalization, and so on. So as you can see here, as we go deeper and deeper into the network, the sizes of the filters also reduce a bit. And we start with filters of large size in the first layers, because this is where the spatial size of the input here is the largest. Then as we go deeper, the spatial size reduces in the network. So as we reduce the spatial size, we can see that we increase the number of feature maps slowly. In the end, you have these two fully connected layers with 4096 neurons each, and then another fully connected layer in the end with 1000 neurons, and this finally then goes into a softmax layer. Here we have 1000 neurons again. This is only because we have 1000 classes in the ImageNet dataset. So here are some key points about the AlexNet architecture. So this was one of the first architectures to stack multiple convolutional layers to obtain a deep network. So this was also the first CNN architecture to use ReLU nonlinearity, and this enabled them to achieve increased speed and accuracy as well, compared to TANH activations, which was mostly used before this period. So in AlexNet, they use local response normalization layer, which normalizes the responses across the channels, but this is not really used anymore because some other papers later on then came and showed that this basically doesn't really have the effect that they initially expected it to have. So they also used dropout on the first two fully connected layers, and they used a lot of heavy data augmentation, such as cropping, flipping, jittering, color normalization, and so on. And even today, these heavy data augmentations are extensively used. So subsequently in 2014 came the VGG architecture that was then a lot different than the predecessors. So the main difference in VGG is that now this was much deeper with smaller filters. So they basically increased the number of layers from 8 that we had in AlexNet to now 16 and 19 layers in VGG. So the way that they were able to do this was that they kept the size of the filters as 3x3 all the way in the network, which also basically is the smallest size you want to go if you want to get the neighboring information. So if you look at the architecture figure here, you will see that it has a very simple structure. So it has these 3x3 convolutions, a pooling layer after every few convolutions, and then the same 3 fully connected layers in the end. You might think, why use smaller filters? So why use 3x3 filters all throughout the network? So the answer to that is that if you start with these 3x3 convolutions, then you have the same effective receptive field as 1 7x7 convolutions. But then you can have more number of filters as we go deeper and deeper into the network. Then you also have fewer parameters, but you can increase the number of filters as we go deeper into the network. However, if you now compare this with AlexNet, we see that VGG has about 140 million parameters, and AlexNet only had about 60 million parameters.
So next we have this UNet architecture, which was in fact proposed in Freiburg by the computer vision group of Thomas Brooks. So here the UNet stems from the so-called fully convolutional network architecture, which we also know as FCNs. And here the main idea in UNet is to supplement the typical contracting network by successive layers where pooling operations are replaced by upsampling operations. So these layers increase the resolution of the output, and the successive convolutional layers can then learn to assemble the precise output then based on this information. So this was first initially proposed for semantic segmentation. We can see an example from the original paper here, and this in fact won the 2015 ISBS challenges by a really large margin, for dental X-ray image segmentation challenge, as well as this cell tracking challenge that we see here. So let's look at the structure. So as we see, it consists of a contracting part and then also an expansive part. So one important modification in U-Net is that there is a large number of feature channels in this upsampling part, which then allows the network to propagate context information to then the high resolution layers. And because of this, the expansive part is more or less symmetrical to the contracting part. And this, in fact, gives this U-shaped architecture that we see in this figure. And let's look at this architecture in a little bit more detail. So the contractive part follows here a typical architecture of a convolutional neural network. It consists of these repeated 3x3, two 3x3 convolutions, which are unpadded, each followed by an ReLU and a 2x2 max pooling operation with stride 2 for downsampling. And at each downsampling step, we double the number of feature channels. And every step now in the expansive part contains an upsampling feature map followed by a 2x2 upconvolution. And this upconvolution is in fact this transpose convolution that we saw in our CNN lecture. And now these 2x2 transpose convolutions have half the number of feature maps or channels, and they are also concatenated with the corresponding feature map from these contractive segments that you see here. And one thing to note is that they do this cropping of the feature map from this contractive part, followed by two 3x3 convolutions and an ReLU. This is at each section. And they do this cropping because there is a loss of border pixels in every convolution. And that's the reason this cropping is essentially necessary. And at the final layer, there's a 1x1 convolution that is then used to map the 64 feature vectors to the number of then classes that you want to classify in the end. So we don't have any fully connected layers in this architecture. And as we see here, they also apply different types of data augmentation strategies to then increase the robustness. And this also requires very lesser number of samples to train this architecture successfully.
Now in 2005, ResNets, or the residual networks, were introduced. So before we get into that, let's take a look at what happens if we start using deeper and deeper layers in simple convolutional neural networks, such as VGG, for example. So here you see the errors of a 56-layer network in comparison to a 20-layer network. And you see the test error on the right and the training error on the left. So first, let's look at the test error on the right. So you can see that this 56-layer network is basically doing worse than the 20-layer network here. But then if you look on the left, the training error, you see the same thing, which is a bit weird. So the network is not basically overfitting, but the deeper network actually has a higher error. So if it was overfitting, you would have found that the deeper network would have a lower error while training and a higher error while testing. So the hypothesis that they came up with is that this was an optimization problem. So deeper networks are harder to train than shallow networks. And the main reasoning behind this is that the deeper model should be able to perform at least as well as a shallow model and not get a worse performance. So motivated by this observation, he et al. Came up with this idea of a residual unit. So now instead of just stacking layers one after each other, where every layer learns some underlying mapping of a desired function, they came up with these residual blocks where we try to fit residual mapping instead of a direct mapping. So you can see the residual block on the right here. So we are going to try to fit a residual to a desired h of x minus x instead of h of x directly. So basically, at the end of this block, we take a skip connection where we are taking our input and we pass it through an identity. So if we have no weights in these layers in between, it's just going to be the same as the output. Now we use additional weight layers to learn some delta for the same residual from our x. Now our output is going to be our original x plus some residual. So how is this network constructed? So we have seen these residual blocks that are stacked one on top of each other, where each of these residual blocks has two 3x3 convolutions. So they use batch normalization after every convolutional layer and only a single fully connected layer at the end of the network for classification. So they have multiple versions of these residual nets for multiple depths, such as 32, 50, 101, and 152 layers, and so on. And for very deep networks that have more than 50 layers, they also introduced these so-called bottleneck units that you can see on the right here. And if you remember, these are very similar to what the Google Net did to improve the efficiency. So they first have these 1x1 convolutions, followed by a 3x3 convolution, and then again a 1x1 convolution after. An interesting fact here is that ResNets actually achieve better than human performance on the ImageNet challenge. Okay, so there are many variants of the ResNet architecture. Here we see a follow-up work from the creators of ResNet themselves, in which they now call it as ResNext. And they want to increase the width of the network by having more structure in the network. And by more structure, they mean that they want to have these multiple parallel pathways, and they call the total number of these pathways as basically a cardinality. On the right here, you see the ResNext blocks with these multiple parallel pathways, and they had up to 32 different pathways like this, as you can see in this figure. Okay, around the same time, there was also this idea of densely connected networks or dense nets. So in each of the dense blocks, every layer is now connected to every other layer in the following network. So the input to this block is also the input to every other convolutional layer in the following block. As you compute the convolutional layer's output, those outputs are also connected to every other convolutional layer after it. And then these are basically combined as inputs to the next layer here. So they advocate in this paper that this alleviates the vanishing gradient problem even more than ResNext, because now you have these dense connections which strengthen the feature propagation as well as the feature reuse. And here they showed that even a shallow 50-layer dense net can outperform a very deep 150-layer ResNet. Okay, so then came this mobile net architecture from Google. Here, the main idea is to use depth-wise separable convolutions to reduce both the model complexity as well as the size. So we learned about these depth-wise separable convolutions in the CNN lectures before. So just as a short recap, it basically factorizes the standard convolution into a depth-wise convolution and then a 1x1 convolution. So I also want to mention that there are many follow-up architectures that go along the same lines, such as MobileNet v2 and the ShuffleNet architecture. And you're interested more to learn about these architectures, then I urge you to take a look at these papers here. Okay, so I briefly want to discuss this recent architecture known as the EfficientNet architecture, since it's very common to use today. EfficientNet is an architecture and a scaling method that uniformly scales the dimensions, depth, width, and the resolution using a compound coefficient. So unlike conventional practice that arbitrarily scales these factors, the efficient net scaling method uniformly scales the network width, depth, and the resolutions using a fixed scaling coefficient. So for example, if we want to use 2 power n times more computational resources, then we can simply increase the network depth by alpha power n, the width by beta power n, and the image size by basically gamma power n, where alpha, beta, and gamma are constant coefficients determined by a small grid search on the original small model, which is the EfficientNet B0 model. So EfficientNet uses a compound coefficient that's called as phi to uniformly scale the network width, depth, and resolution in a principal manner. So I'm not going to go into too much details, but if you're more interested to learn about this, then I urge you to take a look at the paper. So this was basically designed with neural architecture search. The base EfficientNet B0 architecture is the baseline architecture here, and this is based on inverted bottleneck residual units of MobileNet V2 in addition to the squeeze excitation blocks as well. So here in this plot, we see a very interesting plot of EfficientNets after they came out. And here we see the ImageNet top 1 accuracy and the number of parameters. And you can see that by using this compound coefficient for scaling them in a proper manner, EfficientNet achieves the most efficient performance compared to all the other architectures that basically came previously. All right, so let's just review the performance of all the architectures that achieve state-of-the-art performance on the ImageNet dataset. Here we categorize them into feature engineering, neural networks, and deep neural networks. And as we know, AlexNet was the first neural network-based method that won the ImageNet Recognition Challenge in 2012. And as the years progressed, the number of layers got deeper and deeper, and we substantially reduced the error rate. But then an interesting thing happened around here. Basically, the number of layers started becoming more constant, but we can see that the performance still increased substantially by even keeping the number of layers. And you can see that even today, since then, we still have reduced the performance to 1% of error compared to 28%, which was there just about 11 years ago. All right, so this brings us to the end of this video, and I have 3 questions for you. What is the best strategy to take while designing convolutional neural networks? So we went through several of these papers of neural network architectures that were basically trying to tackle this problem. And here I would like to know your opinion on what the best strategy that you think we should take, and what are also some of the methods to keep the number of parameters and the computational burden low. And finally, what are some good practices that we can follow to increase the performance of the model? Here only in terms of the metrics, so I don't want you to think about techniques basically that improve the performance in terms of the computational complexity or the model size, but just the metric, which is the accuracy in this case. So imagine that we have infinite size of computational capacity, and you can train as many as models as possible, and you want to basically only improve this in terms of the metric that you care about. So what strategy would you take? Okay, so I encourage you to pause this video now and to try to answer these questions, and I will see you in the next video. Thank you.